what is called a slab method. So let's take some simple example. It need not be very simple actually. It can be anything. Okay. So we have a three phases. Then what we'll do in this slab method is, so I explain using this diagram. Let's take a horizontal lines through each vertex. Okay. Now this is the, okay, here everything looks very close to each other. Okay. Here actually, here these lines, horizontal line passing through more than one vertex, it doesn't matter actually. So what we did actually here, we are divided this by drawing the one horizontal line through each vertex. We divide the plane into n+1 slabs. This is the first slab, second, third, fourth. Okay. At most n+1 slabs. So given a query point, first identify in which slab this query point lies. Okay. So once you identify this slab, suppose the query point lies within this slab, say slab 6 here. Within this slab, you identify between which two lines it will lie. Suppose somewhere here, query point lies. So you have to identify between these two. And if it is there, and report it is in the part of the F3. So this is the simple method. Is it clear? Any questions here? So what we did, we have to, as a part of the pre-processing, we have to store these slabs. Okay. So slab 1, slab 2, slab 3, and so on. Okay. Within each slab, you have to store these edges. Okay, for example, slab 3, okay, these edges you have to store. Okay. So given a query point, what we'll do, we'll take the y coordinate and searching in which slab it lies. How much time you require to do this one? Identifying the slab in which the query point lies.
Logarithmic by integral.
Yeah, it's simple, straightforward. It's log and time. Okay. So once you identify the slab, within this slab, how you identify this query point? So if you look at one slab, within this slab, you have line segments. Okay, maybe something like this. So we know that actually the query point lies within this slab. Suppose query point is somewhere here. So how we can identify this region where it lies? Can you think of some way of yeah, we can assume that actually this slab is given as a sequence of edges. Okay, say E1, E2, E3, E4, E5 is given, and we also have information actually this phase, say phase 1, phase 2, phase 3. Okay, phase 4, phase 5. This information also there in the part of the slab.
Sir, we can binary search.
Okay.
Like we have the order, so we can take any edge and find whether it is between the edge and next edge or beyond both edges.
Yeah, it is true actually. Even though these lines are overlapping, okay. So these lines actually they're not intersecting within this slab. One important property: these line segments within this slab are non-overlapping. Okay, we can we clearly say that okay, each edge is left of other edge or not, or right of other edge or not. Okay, so we can use the binary search. What we'll do, we'll take the middle edge. Okay, we can say the query point lies left side or right side of this edge. Once we say that okay, it is on the left side, so we can remove all the right side regions actually. So you can remove all the edges which are right of this query edge. So only thing you have to search within this one. Okay. So even though they are actually, yeah, if you take the X projection, they are overlapping. Still, we can use a binary search. We can distinguish clearly that actually with respect to each edge, we can say that query point lies left or right side on it actually, clearly. So we can use a binary search. How much time it takes? Again, another logarithmic time. So overall query time is if these slabs are given, so time complexity of query search is log n. Okay. So now we have to pre-process this given planar straight line embedded graph and create these slabs for the searching process. So what is the pre-processing time? How we can build these data structures of this slab? There's no any special data structure. Simple arrays only we are using. Okay. So one array for each slab, and we also have one array of slabs. So how much time is required to pre-process this to generate these slabs? Any guess?
Order of n log n.
Okay, is good, but how we can do that?
I thought of sorting all the points with respect to y coordinate and then moving around the perimeter in one cyclic order, either clockwise or anti-clockwise, and then processing each edge in those y coordinate orders. So suppose we start at the topmost y coordinate and then suppose we are moving clockwise. So at the secondmost y coordinate there will be a line intersecting that edge. So we will take that segment and store it in the first slab and then continue to other slabs.
But the first slab may be having a more than one edge. No, we have to keep track of all the edges.
While we'll be coming from the like we are moving clockwise, so while coming back, we'll uh, be knowing. Oh,
No,
okay.
yeah, the issue will be there. Yeah, you don't need to have any original algorithm. So whatever we discussed in the class, one of the algorithm can be used here. Can you think of some algorithm which we discussed in the class can be used to generate these slabs? Can we use a sweep plane algorithm for this? Sweeping the plane from top to bottom using a horizontal line.
Sir, but the edges won't be given as edges, right? They will only be endpoints. So
Yeah, doesn't matter actually. Yeah, vertices endpoints are given. That's okay. You try to figure it out whether it is possible to use this sweep plane algorithm for this problem or not. So basically, you sort these vertices from top to bottom, and for each vertex, you also keep a track of what are the incoming edges and outgoing edges, because we are looking at top down. Okay, so for example, for this vertex, okay, we can use the incoming and this is outgoing sort of thing. Just some convent notation, actually, nothing else. Okay. So if you have that information, that easy to you can find out from the doubly connected edge list. It's not an issue at all. So basically, we have to find out what are the edges incident on each vertex, and out of those edges, we have to identify which are actually okay, or for which lines, which segments actually this endpoint, and which new segment is added to this one. So when you sweep line crosses from here to here, so these two has to be removed and this has to be added. Okay. So basically that information you have to keep track. So once we have this one, so you can use a sweep line algorithm. And what will be the time complexity? Hey, everybody convinced we can use sweep line algorithm?
yes, sir.
See what is required in sweep line. So basically we require two data structures, sweep line status and the event queue. Sweep line status is the actually all the line sweepers intersected by the sweep line. Okay. At any given point, actually, the sweep line is here. So segment intersect by this one is actually its status. Whenever it, whenever it touches say, another vertex, you have to output all the edges that are there in the sweep line as a slab. Information of this slab. Okay. Or you can also keep a track of the previous vertex. Okay. So in this case, suppose this is the previous vertex. Okay. So you can keep this information, the y coordinate, and you're outputting the slab again at this one. Okay. So you know what are the edges are there here. You output these things as a part of the slab with this y coordinate and with this y coordinate actually endpoints of the vertices, so that you can do it. Okay. So pre-processing can be done in n log n time. Okay. Of course, not exactly n log n, and or okay, you can, if you say more precisely, n log n plus maybe some k, where k is the size of all slabs. So we have to output the slabs. So sum of all slab sizes is equal to say k. Okay. Yes. Everybody is clear. This k is why this k is coming.
Hello, sir.
Yeah.
Sir, I had a doubt regarding what can be the order of K, sir?
That will come to discuss. We'll discuss that later. Okay. But it's clear. Actually, k is the size of all the slabs.
Yes, sir.
And how much space is required? Space is equivalent to the size of the all the slabs. Okay. Now, question is, what is the size of the k? What is the value of k? In most cases, we can say that it is order n square, because each slab may be containing all edges. Okay. When you say that there are n vertices, number of vertices are n. Okay. So number of edges also become order n. Number of faces also becomes order n. Okay. So everything is linear. So if you look at that, one slab may be containing all edges. So size of this slab is linear. Okay. And we are outputting this n plus 1 slabs, worst case. So overall time complexity or the space required to store all the slabs is order n square. Yes. Is this everybody's clear? That order n square?
Yes, sir.
Okay. So if you generally what we will do actually in this case, we will write pre-processing time as n log n, and space required is order n square, and query time is n log n time. Okay. So it is a very good algorithm in terms of space required, is query time is concerned. We cannot get anything better than log n. And pre-processing also more or less n log n is, no, more or less it's perfect. Because see, if you take a simple n numbers and you want to search for a something, we have to sort them, n log n time, query time log n. We cannot do anything better than these two. So these are the optimal ones. Only thing is we are using the space or n square. That is actually a lot of space. Okay. Of course, there are better algorithms which actually uses only linear space and the same query time and pre-processing time. Okay. But we are not discussing those algorithms because those are little involved one. Okay. I'll skip that part. But in terms of query time and pre-processing time is concerned, this is the best algorithm. Okay. Very simple idea, and you are getting optimal query time, optimal pre-processing time. Okay. Of course, with the okay burden of using the more space. Yeah. Now we are decided that actually the size of all these slabs are order n square. Can you give a one example of planar straight line graph, okay, for which we have order n square space requirement for this slab method? Can you think of one example?
Sir, for order n squared,
Yeah, yeah.
sir, chessboard like grid. Uh, Not a grid, like if every everything is like, yes, like a grid.
See, in grid, they actually see we are to assume that the number of vertices are n. See, your complexity of the planar straight line graph is a linear. I mean, complexity of the planar straight line graph means, okay, in that graph there should be only order n vertices, order n edges, order n faces. Okay, then that is what is called a complexity of the straight line embedded graph. Okay, the sum of vertices plus edges plus faces together. Okay, it is what is called a complexity of the planar straight line graph. Okay, so we have to consider a planar straight line graph in which there are at most order n edges and order n vertices and order n faces. So in chessboard, how many horizontal, how many vertical lines you are considering?
Yes, sir. Then it will not be linear.
Yeah. So we see our input should be linear n. So our input to the algorithm is n, and we are measuring the complex in terms of input. Okay. So that we have to that we should not forget. Yeah, I take a piece of paper and try to draw some polygons or um, some planar straight line embedded graph, so that actually the slab method takes out n square space. Okay, so I myself give an example here. So you can set this one, something like this. Okay, if you have something like this, so if you're drawing a one horizontal line through each vertex, okay. So what is the size of all slabs in this case? Maybe let me draw it more precisely. Okay. So if you consider something like this, okay, so you will have a so many slabs, okay, n slabs only, and if you take the middle one, you will have a n edges, and this above one is say n minus 2, and can below also n minus 2, like that, n minus 4, n minus 4, n minus 6, n minus 6, like this. Okay, so if you sum up all these things, you will get an odd n square actually. So this is the size of each slab. Are you able to see this one? Yes.
Yes.
Yeah, not exactly n. This horizontal and vertical edges won't be part of it. So something like this. So basically, you will have something like this. So in this case, you will get an odd n square. Yes. So in terms of this worst case, this is also as a optimal in this case. Okay. Space required is odd n square. Okay. This is a tight bond. Okay. So I'll stop this here. I'll take up another interesting this thing. Okay. What is called a geometric duality? suppose n points are given in this plane. Okay. So if you want to make some observation on this point set, it's a very difficult to make any observation, because their points are scattered in a space and very few properties you can observe. So instead of that, suppose if you have a n lines are given to us. So this has a more information here. Okay. So in this is what is called an arrangement of n lines. Okay. So arrangement of lines means actually the entire setup. So these vertices and these edges and these faces all together, what is called arrangement of these lines. So if you have to take n lines, what is these n lines are giving to us? These intersection points, the vertices and the edges and the faces. So all these things together, what is called arrangement of lines. So we can use a doubly connected edge list to represent this. Of course, these infinite lines are there. You can always do a bounding box and represent this arrangement within the bounding box using a doubly connected edge list. Okay, so that is a technique what we have used in the computation of one-hand diagram. We same thing. Okay. Now here in this arrangement, we can make some observations. Okay, clearly. So this vertices is formed by intersection of these two lines. Okay, and this edge is part of this line. Okay, like this. But when you look at these points, so we are not able to visualize much geometric properties. So for that, actually, what researchers have proposed is what is called a one transformation, what is called a duality transformation, where the point is mapped to a line and line is mapped to a point. Why? Because to represent a point, we needed two coordinates, x coordinate and y coordinate. Okay, and to represent a line, we require only two parameters. If you use a slope intercept form, m and c. Okay, so only two parameters are required for both of them, either point or line. We use this information to map a point to a line, line to a point. Okay, so this transformation is like this. Suppose if you take a point P, okay, is a coordinate like this. Now we can map this to a line. Okay, y is equal to okay. Similarly, if there is a line is given, and this we can map to a point. So this is the what we call as a primal plane, where actual objects are there. When you apply the transformation, and what you will get is these objects, these are in a dual plane. So this is actually P star, okay, which is the dual of point P. P is a point, P star is a line, and L is a line in the primal plane, and L star is a point in the dual plane. So there is a one-to-one mapping between them. So this transformation is called a duality transformation. Of course, this duality transformation cannot handle, okay, vertical line. So this M can't be infinity actually. That you cannot quantify. If infinity is there, vertical line, the slope is infinity. So you cannot think of, okay, you cannot represent in this fashion. But if there is infinity is there, you can always rotate a little bit and make the slope some finite and make it actually. Okay, so that we can do it. Is that clear? Okay, so this duality transformation has a very nice properties. Okay, so let's see. Take a line L here and take few points on this one. P1, P2, and P3. And if you look at this mapping in the dual plane, yeah, all 3 points meets on a x-axis here. Okay, so this point is corresponding to L star, dual of the line L. And this is the line corresponding to P1 star, and this is the P2 star. So what we can observe here is, if these points are on the line, so in dual plane, these lines corresponding to the dual of these points intersect at the one common point. Okay, so basically it presents the property of incidence. So here this line is, these 3 points incident on the line in the dual plane, okay, and this vertex incident on all the 3 lines. So incident property is preserved. That's one thing. Okay, is that clear? Any questions? See, you can verify using a simple mathematics, okay, whether the incident property is present or not. So it's not a complicated one. Any questions here? Okay, let's look at another property. Let's take another point here. So where the P4 lies in the dual plane, P4 becomes a line here. Okay, say let's say P4 star here. Yeah, if I take this point, okay, so if this point here P4 in the primal plane above line L, in the dual plane L star, which is a point, is above the line P4 star. Okay, so here the above below relation between the point and line is also preserved in the dual plane. Yes? Is that clear?
Yes, sir.
So these are the two important properties. Okay, one is the incident property is preserved, and above below order is preserved. Okay, so using simple mathematics, actually you can verify these properties. Okay, so what is the use of this one? Use of this one is the way I mentioned here. Points are actually here very discrete. We cannot identify much properties. Okay, so in some, when you are solving some problems, we'll map these points to a line. Basically, not only here in this case, actually, we can go to the dual plane and we'll see that what is the properties we can observe in this one dual plane. Okay, for example, you take one point, one problem. Now you take these endpoints here. So between the endpoints, we can define lines. No, between any two points, you can define a line. Okay, so I'm defining a what is called an ordinary line which passes through exactly 2 points. What is there? So endpoints are given to us in the plane, and we call a line is which is ordinary. It passes through exactly 2 points. If third point lies on the same line, then we don't call it the ordinary line. Okay, so yeah, given endpoints in a plane, what are the ordinary lines it has? Okay, so if you look at the same problem in the dual plane, these points becomes lines. Yes, and lines becomes a points. So if some line passing through a 2 points means their intersection point, okay, has only two lines corresponding to points in the primal plane. Suppose you take this line, okay, line passing these 2 points. So let's say they say P1 and P2, and this is say L1. So this P1 is, they say this one, the P1 star, this line, and the P2 is mapped to a P2 star here. And this intersection point is nothing but a L1 star. Yes. So if you look at this arrangement of these lines, look at these intersection points. If each intersection point is defined by exactly two lines, so all those intersection points are actually corresponding to a ordinary lines. If there is any line which is passing through more than any intersection point which is defined by more than two lines, okay, then this is not ordinary line. So by looking at this arrangement of these lines, we can clearly say that actually which vertices in the arrangement corresponding to ordinary line. But when you look at these points in a plane, primal plane, so that difficult to make that observation. Yes. So once we have this clarity and the arrangements, you can use a sweep lane algorithm to report all the ordinary lines, okay, by sweeping the plane in dual plane. Okay, so you will get our n square time algorithm or n square log n. Because we have to process all intersection points, there are n square intersections are there, n log n is what we'll get actually. But if you want to see in the primal plane, in fact, in primal plane also you can do the same thing actually. We are not going to get anything better. Okay, I'll come to that one. So basically, idea of this duality transformation is we can see the problem, whatever the problem is there in the primal plane, that we can map to dual plane. There is a one-to-one correspondence between the problem in the primal plane and problem in the dual plane. Okay, and if you can able to present an algorithm for solving the problem in dual plane, with the same time complexity, we can also present an algorithm for the problem in the primal plane. Okay, so we don't get any extra advantage by going to dual plane in terms of the complexity. You will get a same complexity algorithm, but only advantage what we'll get actually when you go to dual plane, you can able to see some additional properties of this problem, and that helps to solve the problem. That's all. Okay, whatever you can do in primal plane, the same thing can do it in dual plane also. Okay, any questions here?
Sir, could you repeat how did you get the order n square log n thing in the dual plane?
See, given n lines in a plane, you apply this sweep-plane algorithm. Okay. See, sweep-plane algorithm, you apply the algorithm on this problem, you work out all the details, you'll get n square log n.
Okay, sir.
Okay. So I'm not, I mean, see, now as an elective course, you can work out these things. With sweep-plane algorithm, we already discussed 2 algorithms. Okay. So same thing we are applying. It's very much similar to this line segment intersection problem, nothing else.
Okay, sir.
Okay. So you work out, see, this is what you have to do it. In fact, this problem can be solvable in the n square time, but if you use the sweep-plane algorithm, it n square log n it takes. Okay. Any questions? Okay. If there's no questions are there, we'll stop it here. Next week, Wednesday, Thursday, we will have a classes on approximate algorithms. Okay. Pawan will take classes. Don't miss those classes, attend. So I ask one question in the mid-semester. At least one question in the mid-semester. Okay. So see you on Wednesday. Okay.